Okay, good morning, friends, and welcome back to Heat Transfer. So, in the last class, we had completed radiation heat transfer, and I've also uploaded some practice problems for all of you. Not a whole lot, about 10 problems or so. Uh, so please try them, and they're not very difficult, so should be fine. Okay, but as always, any questions, please let me know. Yeah. One more thing, because when while talking about problems, especially Vatsalya, I think you had asked about two of these problems of transient heat conduction. I solved them, and then I left it. I forgot to scan, or I thought I would scan it later and send it to you. Um, Unfortunately, then it skipped my mind. It is there in my office in the department, so I hope I'll remember. As soon as I go back, I'll try to scan them and upload it in the Google folder. It's not Google folder.
Yes.
What is it? Teams folder. Okay. So today what we will do is we are going to start the another topic which is called heat exchangers. Okay. So heat exchangers, that way I was thinking what to do, and is there something that I can complete before the puja break, at least most of it. And I figured out that heat exchangers may be one of them. Heat exchangers, I will also tell you that it doesn't need too much of fundamental theoretical understanding. Whatever is needed in terms of fundamental understanding, you already know. Okay. And to be honest, among all the topics in heat transfer, I would say heat exchanger is one where you have the maximum opportunity for scoring. So every year, of course, this last 2 years things have been different. But before that, I always told students that in your NSEM uh, or in class test, always start with the heat exchanger problem, because there's a high probability that you will get it right away. And in any exam, when you start and you get the first question or the first couple of questions right, that does a lot of good to your confidence. On the other hand, if you start and the first problem itself you face hurdles, your confidence level goes down. So heat exchanger is one such topic that where you can score, and the problems, and however hard I try, cannot be very difficult. That is based on the things that we are going to learn as part of this course. However, heat exchanger is possibly the most wide application of heat transfer. You find heat exchangers everywhere. And why? Because as we will see in the very first slide that I'm going to project today, heat exchanger is about, as the name suggests, it's about exchange of heat. Exchange of heat between a hot fluid and a cold fluid. And you require that everywhere. If something is hot, you need to cool it down. If something is cold, you need to heat it up. Okay? So that's where heat exchanger becomes important. Your car radiator is a heat exchanger, where the hot fluid is your engine oil, and the cold fluid, sorry, where the hot fluid is water, that in turn cools your engine, and the cold fluid is air, okay, which is blown by your fan. Okay. It is known as car radiator. It's a misnomer. It's primarily a heat exchanger, and the main mode of heat exchange is convection, not radiation. Okay, but it's called radiator. In your air conditioners, both indoor and outdoor unit is a heat exchanger. Okay, what you read as evaporator and condenser, these are heat exchangers. Okay, the room heater that you have, that's also a heat exchanger. Um, Geysers is not essentially heat exchanger the way we use it. the water, because there is a heating coil and the water gets warm. But when you need to heat up large quantities of water, it is again heat exchanger. You pass some hot oil through it, some pipes containing hot oil, and the water gets heated. Okay, so lots of things. And again, in power plant, process, chemical industry, heat exchangers are everywhere. Okay, so with that, with that introduction, let me get started. I hope you are. What I wanted to say is that heat exchangers is extremely important topic. Okay. So what I will do is this will be a more hybrid mode. There are certain things which I'm going to show in slides, and then certain derivations, problems, etc., which I'm going to do in the whatever the equivalent of the blackboard, which is my writing tablet. Now, what is a heat exchanger? As I said, these are devices where heat is transferred between two fluids at different temperatures without any mixing of fluids. Okay. So look at the underlined portion. Heat is transferred between two fluids, and the last part is without any mixing of fluids. Okay. Now the last part is not 100% valid, because there is certain types of heat exchangers which are called direct contact type, where there is actually mixing. So there can be mixing. Okay. All right. So this is heat exchanger. Now heat exchanger, if you now think of it, how does a heat exchanger look? If you ask me, there are just variety, numbers of heat exchangers. There are different designs, different geometries, flow configurations, materials, etc., etc. Okay. So are you guys all there? Can you see my screen? Hello?
Yes, sir, but we can't see your presentation.
No,
Sir.
no, right now it's okay because I stopped the slideshow. Because I heard a couple of this bong sounds, which I thought that typically happens when the connection goes off and it's trying to reconnect. Okay, good to know that. All right, so let me go back again and resume the slide. Okay. So if you talk about classification of heat exchangers, there are like thousands uh, of different configurations. So if you ask me how does a heat exchanger look like, I won't be able to tell you. Okay, I'll be able to tell you some of these. I won't be able to give you one definite answer. By the way, Professor P.K. Das, who is in our department, who used to teach heat transfer along with me for several years, he is, I would say, pretty much a national authority on heat exchangers. Okay. Very few people within India know heat exchangers better than he does. I don't know if he has taught you either thermofluids 1 or 2. He's one of the stalwarts of overall heat thermofluids in India, and definitely probably among the very best when it comes to heat exchangers, heat exchanger networks, etc. All right. So for this course, we are going to primarily focus on one type of heat exchanger, which is called the direct transfer type. What is it? I'm going to talk about that. And I'll just allude to two more different types, which is called storage and direct contact. Okay, because you should know what they are, just basic definitions. So look at this. What is direct transfer type heat exchanger? I'll read the definition first, and then we will dissect that sentence. Okay. It is that type of heat exchanger where the hot and cold fluids flow simultaneously through the device and heat is transferred through a wall separating the fluids. Okay. So the first thing is the hot and cold fluids flow simultaneously. Very important. The flow is, now that is true for most heat exchangers that we see around us. That is true. So there is a hot fluid, there is a cold fluid, both of them are flowing, and then the heat is transferred between them through a wall separating the fluid. So the best way to understand this is to look at this picture. Okay. As you can see, these are two circular tubes. Okay. Through the central one, there is a cold fluid that is flowing. And through the outer, what we will know later as shell, there is a hot fluid that is flowing. So what happens? During the heat exchange, the hot fluid, which is on the outer shell, loses heat to the cold fluid that is flowing through the inner tube. Okay. So as a result, what happens? The hot fluid, by the time it comes out, it becomes cooled, and the cold fluid, when it comes out, because it has absorbed heat from the hot fluid, hot stream, it becomes hotter. Is that clear? Any question? So as you can see, this is my hot fluid. Let me call it, and these are nomenclatures that we are going to use very often. PHI, hot inlet, and this is THO, or sometimes THE, either outlet or exit, whichever you talk, whichever way we define it. This is TCI. This is TCE. Let us use E for inlet and exit. Okay. So the cold fluid heats up, the hot fluid cools down. The second type we call it is a storage type heat exchanger. Now, what is the difference? In the previous case, in direct contact type, we said that the hot and cold fluids move simultaneously. In storage type, it doesn't move simultaneously. Okay. So what happens? The heat transfer happens through a coupling medium. Okay. So the heat transfer between the hot and cold fluids occurs through a coupling medium in the form of a porous solid matrix. The hot and cold streams flow alternately through the matrix, the hot fluid storing heat in it and cold fluid extracting the heat out of it. Okay. So what do I mean by that? Now let us look at this sketch on the left hand side and try to understand what we are trying to say. So let us say it's an enclosure filled with a porous matrix, and there are 4 points, okay, inlet, outlet, whatever you call it. What we are going to do is we have named it A, B, C, and D. So A and B, what happens is at the beginning, there are 4 valves attached to it. At the beginning, I'm going to open A and B and let the hot fluid come inside this enclosure, which is filled with this porous matrix. So the hot fluid will come in, flow through this porous matrix because it's porous, so it will let a liquid flow through it, and the hot fluid will come, flow through this, and get out. Yeah. Then what we do is we close A and B. The hot fluid can never, it cannot flow anymore. So now what we will do is we'll open up, we close A and B, and we open up C and D. The hot fluid, while moving into the through this porous matrix, has given up the thermal energy, at least part of the thermal energy, to the porous matrix. Okay, the porous matrix was cold. So when the hot fluid started flowing through this porous matrix, it rejected the heat. It gave up its heat or thermal energy to this porous matrix, which in turn now gets heated. Okay. So what can this porous matrix be? It can be, let's say, a packed bed of stones or rocks. Okay. Why? Because these stones or rocks have a very high specific heat. Okay, they're heavy, so they have more mass per unit volume. Their density is high, plus the specific heat is also high. So therefore, for a certain increase in temperature, they can store a lot of heat. MCP delta T, right? If the porous matrix was initially, let us say, 30 degrees C, and then the hot fluid flew through it, and then the temperature goes up to 50 degrees. So the mass times specific heat times 50 minus 30, that's the amount of heat in joules which is stored in this matrix. Okay, stored ho gaya. Then A and B are closed, and we will now go to C and D. We will open up C and D now, so that the cold fluid now comes through it, comes through C, flows through, and comes out of D. So while doing so, it picks up the heat from this porous matrix. Okay. So the heat that was stored by the porous matrix from the hot fluid is now given up to the cold fluid. So what is the difference here? The hot and cold fluid streams did not flow at the same time. And there may be a gap of several hours or even a day, maybe, depending on the application, between the flow of hot and cold fluid. Okay. So needless to say, in a real application, you will insulate the porous matrix, this box, quite a bit on all sides, so that the porous matrix, when it stores the heat, doesn't lose it to the ambient. But well, that's different. But at least from the type of construction of this heat exchanger, this is how it works. Okay. All right. There is another type which is called the heat recovery wheel. Here, what happens is the porous matrix, let's say it's like a honeycomb structure, as I have shown over there. This wheel can rotate. The hot fluid flows to the top half, the cold fluid flows to the bottom half. So what happens? When the hot fluid flows to the top half gets heated, right? Because it absorbs the heat from the hot fluid. But when it rotates and comes down, it rejects that same heat to the cold fluid, which now becomes hotter. Okay. So this is also storage type, in the sense that the heat is stored by this rotating wheel, by one half of the rotating wheel, and rejected in the other half. However, the difference here is that the fluids move simultaneously, moves at the same time. Keep that in mind. So therefore, especially for heat recovery wheel, the fact that the hot and cold streams flow alternately through the matrix is actually correct. Because if you take the matrix, the definition to be a certain portion, yes, that portion, the hot and cold fluid are moving alternately. Okay, so that is why this uh, heat recovery wheel can be classified under storage type heat exchanger. It's also called a regenerative type heat exchanger. Okay. The last one we are going to talk about is called the direct contact heat exchanger. Okay. So here the two fluids actually come in direct contact. What does it mean? It means, let us say that I have, let us say, a towel like this, okay, which is filled with cold water, and I'm passing hot oil. I'm pumping hot oil from the bottom to the top. Possible? So the two fluids come in direct contact. They are not separated. But because oil and water are immiscible, they do not mix either. The oil will come up partly because it is lighter than water and partly because it is pumped. So it has got some momentum in the upward direction. The oil will come up, the water will come down. Okay. The oil will lose heat to the water. Therefore, the water during its flow will heat up, the oil will cool down. Now, oil and water, I said about two liquids. I specifically meant that because these are immiscible liquids. However, most direct contact heat exchangers happen between a gas and a liquid, which is most common. The gas is either bubbled through the liquid or the liquid is sprayed in the form of droplets into the gas. Okay, as shown here. You can see there's a water line in this picture. The water is being sprayed from the top and some hot gas is coming from the bottom. So the hot gas will cool down and come out from the top. The water will heat up by absorbing heat from the hot gas and come out as hot liquid from the bottom. So this is a direct contact heat exchanger. Now, one, I will mention that there is another type under direct contact, which we call direct contact condenser. What is it? Let us say that this gas that we are talking about, this red hot gas which is coming from the bottom, that is actually steam. And you spray water from the top. Right? And the temperatures are such that you adjust the flow rates, temperatures, whatever, everything such that the steam actually condenses. It not only cools down, but it also condenses. Then what will happen? The steam will condense, and both the water sprayed from the top as well as the condensed steam will come down from the bottom. Right? So that is called a direct contact condenser, where here the two fluids are miscible, right? They can mix. Okay. So direct contact condensers are also common. In your power plant, you may have, I don't know, probably you will study or you may have studied about cooling towers. That is an example of direct contact condenser. Okay. All right. So this storage type and direct contact type, this is good enough for you to know what they are. If somebody asks you in an interview, okay, what do you mean by a storage type heat exchanger? You should be able to tell them. But in terms of further construction, analysis, details, etc., we are not going to cover as part of this course. Our focus will be on this one, which is direct transfer type heat exchanger. Direct transfer, direct contact. The names are very, very similar and close, but they mean completely different things. Okay. All right. So 3 types of heat exchangers. Any questions? Is everything clear? Come on, that cannot be. No questions. Everybody's awake, right? Huh?
Yes, sir.
What is that? Yes, sir. You have understood everything or you're awake? Or both?
Both.
Both. Okay. Okay, that's reassuring. All right. Okay, 8:30. Let's move on. Okay, now we will come to the actual crux of this course. And others are also important, by the way. But now we are now going into a little deeper. Direct transfer heat exchanger. So here, there are many types of designs possible. I have listed some of them. And if nothing else, at least you should know these names. Name dropping always helps. If you're, for small, short interactions, name dropping helps. Longer interactions, be careful. When I had a friend who was very impressive to talk to. Okay, but it came to fundamental understanding, funda, and all that. A bit superficial and shallow. So we used to joke that if you get 5 minutes to interact with someone, he will impress that person much more than what rest of us can do. But if that 5 minutes become 10 minutes, we cannot stay. So, so those are good skills, very important skills in life. How much you can impress people in short interactions. But it can take you to some extent, but not beyond that. All right. So direct transfer type heat exchanger. These are some of the types. So let us take one by one. This is just a list. The first one, I'll keep it very simple here, and we will talk about them. First one is called concentric tube. The name suggests, it means 2 tubes concentric with the same axis, same central axis. But to be honest, it doesn't have to be central, coaxial, or concentric. Okay. Again, what is it? As we discussed, there is one fluid that flows through the center. There's another fluid that flows to the outer side, outer tube, one flows to the inner tube. And there is heat transfer through the wall of the inner tube. Okay. So many times we write it like this. This is the inner tube. And then this is the outer tube. The fluids don't mix. So this is mass flow rate m dot c and mass flow rate m dot h. Okay. So how much heat will the hot fluid give up? We can write it as m dot h times Cp times THE minus THI. If the hot fluid was entering at a temperature THI, sorry, it is coming out at a temperature THE, then this is the amount of heat that it has given up. That is also going to be the amount of heat that the cold fluid picks up. Okay, so this is m dot h Cph, m dot c Cpc. Cold fluid Okay, I think I should write it the other way. So this one is THI minus THE. This is TCE minus TCI. So this actually is the fundamental equation of heat exchanger, heat balance, that's it. The amount of heat given up by the hot fluid is equal to the amount of fluid that is picked up by the cold fluid. So in the most simple or simplest type of problems, you will be given everything and then you will be asked that okay, and the hot fluid temperature is given at the exit and inlet. And then you will ask that okay, can you tell me the temperature rise of the cold fluid? Or even if the cold fluid inlet is given, what is the outlet temperature? So basically, out of 4 unknowns, 3 unknowns are given, and you have to find the fourth temperature. That's the most simple type, but we do use it. Okay. So this is one of the most fundamental equations of any heat exchanger actually, irrespective of the type. Because see, we are not talking about how the heat exchange is happening inside. What is the construction in it? So this m dot Cp delta T of hot fluid equals to m dot Cp delta T of cold fluid is true for any heat exchanger, not just the concentrating tube. I used it here because it's most easy to visualize. Okay. Next one is called shell and tube. This is a very common type of heat exchanger, especially in power plant or process industries. Okay. So actually, if you think about it, this is also a shell and tube. Okay. But we talk about shell and tube a little differently here because these are like monstrous type heat exchangers, huge. I mean, the whole room can be one such heat exchanger. And what happens here is the tube, the inner tube that I was talking about in the previous one, actually has a bunch of tubes like this. It's a bundle of tubes. Okay. So if I take a projection plane through a cross section, this is how it looks. The hot fluid comes in from here. I marked it as, this bright crimson red. And the hot fluid then flows through these inner tubes and then come out to the outlet. This is actually your PHI and this is your PHE. Okay. And from the color, you can see that it has changed from very bright red, something which is pinkish. So therefore, the temperature has gone down. Okay. Why did the temperature go down? Because it gave up heat. Gave up heat to what? Or to whom? It gave up heat to a cold fluid which flows through this outer shell, which is coming from here, flowing through this shell and coming out of here. So this is TCI, this is TCE. So therefore, from the color also you can see it came out at a more darker shade of blue, and it came in at a darker shade of blue and is leaving at a lighter shade of blue. So the temperature has increased. Okay. So when this fluid is actually flowing through this outer shell from a left part to the right part, it's called one pass. Okay. Similarly here also, the tube also, it's one path from the right to the left, coming from the right, traversing once, leaving from the left. Okay. And the cold fluid coming from the left and leaving at the right. Just once. Okay. So we'll come to that. But look at one more thing which we are calling something called baffles, as you can see in this picture. What are these? See, for better heat transfer, you would like the fluids to remain in contact for a longer period of time. Okay. Otherwise, what happens? The hot fluid will come in, find the path of least resistance, and leave to the outlet. So how do I make sure that it doesn't do that? It stays inside, and the residence time is increased so that there is more heat transfer between the hot and cold fluids. In order to do that, we add these things called baffles. Baffles, these are just plates that does not traverse throughout the cross section. So as you can see, the cold fluid, while after coming, has to go through this zigzag path. It could not go directly like this. It was not possible. So therefore, what it has to do is it has to go like this, and then come out. Right? So the baffles actually make the path more tortuous and increase the residence time. Okay. Now, how does it actually look like? You see a picture at the bottom. You probably still don't get a feel of the size, but this can definitely be anywhere between like 10 feet in length and what, maybe 3 feet in diameter, 2 feet in diameter. Some of the larger ones are even larger, very big, maybe 6 feet in diameter. And you cannot even stand. I mean, at least I cannot. Okay, so this is how it looks. It's actually in the 3D. There is a bundle of tubes inside, and then you also see these baffles. You see the baffles that start from this end. So you see 1, 2, and 3 of them, and then you also see here these baffles, right, which do not come right till the end of this. I mean, it doesn't come right till this end, but the end point is somewhere in the middle. That is what I was talking about. It doesn't. These baffles do not extend fully, right? Because if it extended fully, it would have blocked the entire cross section. The cold fluid would not have been able to move. Clear? Does everybody understand the construction?
Yes, sir.
Okay, good. So shell and tube, what are the different types? The first one you see, as I was talking about, the picture we saw, it is called one shell pass and one tube pass. Okay, pass means just one time from left to right or right to left. Okay. Whether it is flowing inside, whether it is flowing through a tortuous path, etc., we don't know, and we don't care also. The fact is, the fluid actually goes only once from left to right. That's what one pass is. So it's one shell pass and one tube pass. The second one you see here, and the left, it's one shell pass and two tube passes, because inside the tube, as you can see, it enters from here, it goes, takes a 180-degree or U-turn and comes out. So therefore, it has traversed twice, right? Once, twice. So that's why we say two tube passes. Shell pass, still only one. Okay. Look at this one. There are two shells. So therefore, two shell passes. One, the top shell, it comes from the right, from here. Okay. Then comes out and again it goes from left to right in the second shell and comes out. So 1, 2. That's why 2 shell passes. And tube, 4 tube passes. Inlet. First from left to right, again right to left. Sorry, yeah, right to left to right to left to right. So you can see this like 2 shell passes, 4 tube passes. So this is how we classify. If somebody asks you, I have a shell and tube heat exchanger with five shell passes and 10 tube passes, so you know exactly how it looks like. Okay. Next, we have something called a parallel plate heat exchanger. It's a little difficult to visualize, but I think this animated GIF on the left, bottom left, will help you to visualize what it is. So these are parallel plates which are brought very close to each other, but it's not like they're stacked right on top of each other. There is a gap between two adjacent plates through which a fluid can flow. Okay. So in the first gap between plate 1 and plate 2, you have hot fluid. But plate 2 and 3, you have cold fluid, and so on. So between two adjacent gaps, you have the hot and cold fluid circulating. Okay. So how does this happen? So the hot inlet water comes in from here. Let me use the laser pointer. So as you can see, the hot fluid is coming from here, and then it cannot go through. This path is blocked. Okay, you see this path is blocked. It cannot go straight. So therefore, what happens? It has to come down and come out like this. Okay. The next one, it cannot get into this the second gap or the gap between second and third plate. It has to flow through. But again, it gets a chance to flow through the gap between third and fourth plates and come back. Okay, and so on. So between the gap between 1 and 2, then 3 and 4, then 5 and 6, then 7 and 8, and so on. And it takes a U-turn and comes back. The cold fluid, exactly the opposite. It enters, it doesn't get a chance, it has to flow straight, doesn't get a chance to get into this gap between plate 1 and plate 2, but finds an opening in between 2 and 3. Again between 4 and 5, again between 6 and 7. So as you can see, that is what you see here at the bottom left part. Okay. So these are parallel plate type heat exchangers. The heat exchange happens through the walls of these plates, on one side of which you have flow of hot fluid, on the other side you have flow of cold fluid. And finally, we have this configuration called extended surfaces, what you see here. Okay. So here what happens is, again, the flow of the first fluid is through the tubes, and then the second fluid is through some fin. Okay. I could have had the flow just above the tubes, right, like I had in the shell. But if I want to improve that, improve the surface area, then I can attach these fins, which we had studied before in conduction. These fins are attached to the tubes, maybe carrying the hot fluid. So they can conduct the heat out as well and increase the surface area across which heat transfer can take place. Okay, so you see flat tubes and circular fins, etc. Okay. In the bottom part, you see this. There are finned heat exchangers. These are all finned passages at right angles, right? From, let us say, in one direction, let us say south to north, you have one fluid, and from west to east, you have a second fluid. Okay. And then you can also have serpentine paths, right? It doesn't just go from south to north. It is forced to come back and go. Again, it finally goes from south to north, but not in a single pass, multiple passes. And same thing west to east as well in multiple passes. Yeah. The last thing I would like to talk about is something called a cross flow. Okay. The cross flow time at this point will, I mean, you can understand in the sense that the hot and cold fluids are flowing at right angles. In the pictures before, they were both flowing in the same direction, right? Left to right or left to or right to left or left to right. Okay. Sometimes they are flowing, both were flowing from like here. The hot fluid is also moving. The cold fluid is also doing the same. So here we call them co-flow or parallel flow. But I could have had the other way also, the way I have drawn here at the bottom. The cold fluid moves from left to right, the hot fluid moves from right to left. This we call counter flow. Okay. So parallel flow, counter flow. And what I'm going to talk about here is called the cross flow, where they are at right angles to each other. So under cross flow also you have both fluids mixed. You have this concept of mixed and unmixed fluids. It is essentially what it means is when you have flow through multiple tubes and the tubes are not mixed with each other. I mean, these are parallel paths that do not interact. It's called unmixed fluid. And so what you see on the left hand side, the fluid flowing through the tubes is also unmixed, and the flowing through this parallel fin passages are also unmixed because the air that is flowing through the first passage doesn't interact with that in the second passage and so on. However, if it's just a shell and no fins, then the second fluid which is flowing through the shell is mixed. Okay. So you understand, I'm just looking at this picture, you know, and there's not much to explain here. Okay. All right. So it's 8:54. So let's take a break now. What we have done is we have pretty much covered the very basic fundamental initial concepts of heat exchangers. Okay. I'll share these notes. But what we will do is now we will move on to the conventional method. And we are going to talk about, we're going to do some more mathematical treatments now, starting with these topics. Okay. All right, where you have to refer to your class notes. So let me end the slideshow here. We'll go back. This card, I don't want patience. Okay, and let me stop sharing the screen. So we will come back in 5 minutes and continue with our discussion on heat exchangers. Okay, so okay, all right, thank you. Stop the recording now.